Okay, everybody. So last time I think we stopped at this point, around this point. We said that these are some of the functions that are from the POSIX thread library. It's like, I mean, well, it looks like it is different from making a new process and managing it, but actually it is very similar. Instead of using fork, we use a create. But create takes, what are the parameters for the create? Create takes a structure for the thread. Also, it takes, like in this case, it takes a pointer of a function. Here, the print hello world is a function name. Of course, it's a function pointer too. And it takes the function pointer and the parameters to that function. And that's how the create works. And we have the other stuff like terminating a thread, okay, waiting for a thread to end, and yielding your CPU to some other thread. And these are for the attribute initialization and the maintenance, etc. And we looked at this simple program. When we looked at this program, we said that when you run such a program, there is a loop from 1 to, I guess, 10. It runs from 0 to 10, right? It runs from 0 to 10 here. And it creates 10 threads. Each of the threads are very simple, actually. They are just printing this message and just terminating themselves. But what I said is that we don't know the order of the threads that are going to print this message, saying that I am thread number such and such. You may see that sometimes the thread number 1 prints this message before the thread number 2. Sometimes thread number 7 prints this message before thread number 5. We don't know, okay? Because, I mean, once you make your threads, once your threads start running, the scheduling is done by the operating system or the thread library. So it is not in your hands anymore. You cannot know the order of the execution of these threads, and you cannot know when it's going to switch from one thread to another thread. That's why writing parallel programs, multi-threaded programs is not that easy if you don't know what you are doing. If you know what you are doing, of course, I mean, if you are disciplined, if you are writing your using certain rules, then you should be fine, but it is not as easy as writing sequential programs because you don't know the order. Sometimes, I mean, you may say that what is wrong with not knowing the order? Well, I mean, if you are communicating between two threads, then, I mean, using the same common memory position location, then that's going to create some problems, and we call those problems as race conditions. And we are going to look at those race conditions, as I said, for most of the part of this chapter. Okay, so we looked at this one, and we stopped at this point, and now I'm going to talk about how we can implement the threads. Are there any questions so far? I mean, so far for the chapter? Yes?
The trade is code block errors and numerical, linear increments for the I.
Yeah, I is incremented one by one.
Yeah. How you cannot know which one is?
Well, the order of creation is the same, but you may not know if what does this do? It says that hello world, greetings from thread number 1 and thread number 2 and thread number 3, right? As soon as you make these threads, let's say you made 5 threads, okay? They are all ready to run. There is only one CPU. Okay? Which one is going to be picked to be run first depends on the scheduler, thread scheduler. Okay?
That depends on the creation time.
Yes. Well, I mean, if your scheduling is based on the first come, first served, maybe it is the creation time. But if it is not, if it is the one that is closest to me or the one that has the most amount of cache space, I don't know, I'm just making this up. So, I mean, it depends on the thread scheduling algorithm, and we don't know what that algorithm does. I mean, if you are careful, if you are clever, maybe you can dig it up for Windows. For Linux, it might be different. For different systems, it might be different. So there are no assumptions about the order of executions or order of scheduling for this kind of stuff. You cannot know. There are many things changing. Okay, that's why I am saying that I don't know which print hello will come first. It might be the first one, second one, fifth one. I don't know. Okay. Because, I mean, as I said, I have only one CPU, and at the end of all the creations of these threads, there are a total of 11 threads running. One is the main thread. The other 10 is the created threads, and it is up to the thread scheduler to run whatever it wants. Okay. Sometimes those decisions are made randomly. Sometimes there are some rules, etc. Okay. So let's look at this. If there are no other questions, let's look at the implementation of the threads. Okay. There are basically three ways of implementing your threads. The first one is the user level one, is the earliest thread implementation method. Okay. They have implemented threads in 1980s like this. Later they realized that maybe we can get the kernel involved, and that will make the things a lot easier for us for some cases. And then there are some hybrid implementations between user level and kernel level and schedule activations and etc. We are going to look at these later one by one. Let's look at this picture. Okay, this picture is nice. This one talks about implementing threads in the user space or the kernel space. Let's look at this picture. This is the user space one. Okay. These are regular pictures. Process number 1, process number 2, P1 and P2. There are 3 threads inside process number 1. There are 4 threads inside process number 2. Okay. When you implement your threads, your thread library, remember these functions. Okay. Remember these functions. Of course, these are the functions to be implemented by somebody. Whoever has implemented this pthreads library, if they have implemented these functions without referring to the kernel at all, okay, I am always in the user space. I am always in the user mode. When I create a new thread, okay, I don't tell anything to the kernel. I handle everything myself. What does that mean? That means that I need to keep this thread information, okay, this thread information inside my process, I get this blurry, do this maybe, and then this, no. It took it in the buffer and it is not letting me. I know how to solve this. Okay. Maybe I didn't know how to solve it. Okay, good. So, yeah. So, this process has to do everything itself inside the library library functions. So it has to keep a thread table, and it has to do the thread scheduling, it has to do everything about the threads, and the kernel doesn't know that there are three threads running inside this process. Okay, so lots of job for a library, but even this is very similar to the process scheduling and process creation, etc. Operating system used to do these kind of things for me, for the processes. Now I am saying that I am going to do this process creation, process termination, process scheduling inside this process, and the kernel will think that I have a single process, and I am doing something inside my process. It doesn't matter what I am doing for the kernel. Okay, so this is called implementation of the threads at the user level. Okay, possible on most operating systems, even the ancient ones. The operating system doesn't have to support the threads. Okay, because mine is just a regular program using a specialized library named pthreads, and that's it. That will be the whole thing. And you might think that, well, this is not a very good thing because threads are kind of special. They need some privileged instruction, etc. In fact, no. I mean, threads are regular executions whenever they need, for example, open a file, read from network, etc. They make a system call, and the kernel answers that, and they will continue, right? So no problems for that one. That's why this is a nice solution if your operating system doesn't support threads. Okay, so I have implemented everything myself inside my process. Of course, I mean, it is not that easy to switch from one thread to another thread because you need to save the stack pointers and all the registers, etc. Remember how to switch from one thread to another thread. Okay, we need those, but I mean, I can write those parts in assembly. This is my process. I can do whatever I want. So this is called user space implementation of the threads, and it has very nice, actually, advantages. And of course, like everything, it has some disadvantages too, and we are going to look at them in a few minutes. Okay, so with the user level threads, auto thread creation, destruction, scheduling done at the user level without asking anything from the kernel. Okay, and to create a thread, okay, our thread library must allocate storage for stack, program counter, and etc. Of course, most of these things done using assembly. Okay, when a thread yields the CPU, of course, our schedule says that, okay, this thread yielded the CPU, the other one will continue. And the thread schedule, again, it is implemented inside the process. Okay, the scheduler runs in there, etc. Okay, so this is how it is implemented. Very nice. The nicest feature of user level implementation of the threads is that to handle threads, either creation or scheduling or that kind of stuff, no context switch is needed. Why? Because I am handling everything inside my process, right? I am not asking operating system to do something for me. Okay, I am not asking operating system to do something for me. All I am doing is running some specialized library routines within the same process. So no context switch, no system calls needed. Okay, no copying of data across the boundary, protection boundary, which is the trapping to the kernel. And since I am in the same address space, most of the time, I don't have to flush my hardware memory cache. So these are very nice features. Threads are already fast, and implementing it this way makes them even faster because I am not asking anything from the operating system. These are the efficiency gains. Other advantages, okay? I can write my own scheduling algorithms for my threads, okay? I can say that this is a special thread. These are not that special, so this has a higher priority, and etc. So I can come up with any kind of scheduling algorithm for the threads of this process. For the other process, this process might say that, okay, I'm going to use another scheduling algorithm. I just invented it. Since these are all my libraries, I am not asking anything from the kernel. I can do whatever I want with my threads. Okay, so specialized thread scheduling algorithms are possible with the user level implementation of the threads. For example, in Java, you remember there is a garbage collector, right? Garbage collector is usually a thread. Okay, it runs from time to time, but it's a specialized thread. Okay, and I am scheduling it myself at the Java virtual machine level, so it makes it possible to write this kind of stuff, and they scale better than other types of threads and etc. Okay, so these are all the advantages, but what are the disadvantages? Okay, in operating systems or in any parts of the engineering or science, you don't always talk about the advantages. There are some disadvantages of everything. Okay, there are some disadvantages of everything. I mean, you cannot say that we don't know that there are disadvantages of such and such thing. There are disadvantages of everything. So what would you think that the disadvantage of such an implementation would be? Am I going to run into the same problem again? Something is cached. It thinks that it is using the correct thing from the cache, but it is not. Do the same thing again. Okay, I think this is what's happening. I am not terminating this process correctly. I think there is a part of this process running somewhere. Where is my draw board? Do you see it? No, it is not there. Maybe here. Get rid of some of the other stuff. Okay. Couldn't find it. Maybe it is here. No. Okay. Let me close as much as possible. It's not an operating system thing. It's a application thing. Okay. Maybe I have too many open files. Could be. Okay, so tell me about the disadvantages of possible disadvantages of such implementation. Well, the opposite side is just the kernel level implementation. Everything is implemented by the kernel. So to make a new thread, okay, you make a system call, and to terminate a thread, you make a system call. So everything is handled by the kernel. So that's the way of implementing it at the kernel level, and I am saying that it looks like implementing these kind of stuff in the user level has many advantages, and it looks like there are no disadvantages. One might say that the protection might be a disadvantage, right? Because all the threads are implemented inside the same process, and if I mess up something, so all the threads are going to go. They will all die because this thread table and everything inside, they are all in my other space. Okay, so that might be a disadvantage, but the thing is that, I mean, threads are sharing their memories anyway, and if I mess up something with one of the threads, yeah, all the other threads are going to be affected. That's true, but They are helping each other anyway, and if one of them is dead, the others will not be useful much. So the situation would not be that different if I have implemented threads with by the kernel. Okay. So the protection is no. I mean, there is no protection between the threads, as you know, right? I mean, there is no protection between these three, and there is no protection between these four. Okay. So that's not it. But there is a very serious problem with this approach of implementing the threads.
Thread table is on the kernel level, right?
Well, thread kernel in this picture.
Yeah.
Kernel doesn't know anything about the threads. There is no word such as thread for the kernel.
So
In this case, yes, but I am asking about this case. What is the disadvantage of implementing threads that way?
So this is not a problem. I think this is a problem that kernel doesn't know anything about the.
So what is the problem?
For example, priorities of the threads. It doesn't know anything about the threads.
So why do I care?
So maybe one of them is fault. And
One of them is what?
one of the threads is died, for example.
So
The priority of the others.
so
should
that
know
that's
about
even
the
that's
kernel.
even better. Since I am adjusting all the priorities inside this process, I am more flexible. I can do whatever I want. I am not relying on the kernel to make those kind of priority adjustments or the scheduling. I am doing my scheduling myself. This is even more flexible. Otherwise, I do whatever the kernel tells me to. I mean, kernel says that now you are going to run, now you are going to run, and etc. I don't have much control over that. But if I am scheduling everything inside my thread table, okay, then that's much more flexible than the other ways. But there is a very serious problem with this approach. I think it is related to what you are saying, but it is not exactly the same thing. Anybody from the online audience? How many people do we have here? Well, 80 people, good. Let's think about this, okay? The kernel doesn't know that there are 3 threads running, okay? Kernel just doesn't know that. Yes?
If the process dies, the whole thread will go, and kernel doesn't know anything about it.
If one of the threads is, say it again.
If the process is died, and the kernel doesn't know about any threads, I guess.
You mean if the whole process dies, then the whole process dies. I can't do that in any of these pictures, right? But if one of the threads, let's say this thread needs to read data from the disk, okay? To read data from the disk, what you need to do, you need to make a system call, right? I made a system call to the kernel, okay, trapped, okay, I got what you need. I am going to load it from the disk, and I am going to block you because the data is not ready, okay? So the kernel thinks that, okay, process 1 is a single threaded process, okay? There is only one execution. So kernel blocks the whole process, and it makes you wait until the data is ready. When the data is ready, it unblocks you. But the thing is that only this thread should be blocked, not the other 2. But the kernel doesn't know about them, right? I mean, this thread and this thread is ready to run. They can use the CPU because they have things to do. But kernel will block me because kernel thinks that, okay, there is a single thread running inside this process, and there is a single process running in this process, and it just needs data from the disk. and the data is not ready, I'm going to block this process. If this whole process is blocked, then this scheduler cannot run. Because the scheduler is a program too, right? It's just a separate scheduling thread, okay? This one will be blocked too. So the whole process is blocked. Even though I can continue running, I can continue using the CPU, it will not happen because kernel doesn't know what's going on inside this process, okay? The similar kinds of problems are valid there. For example, let's say on my computer I have four processors, okay? Who allocates the processors? Of course, the kernel allocates them. As a regular program, I cannot do the processor allocation. I know that there are 3 threads inside this process, but the kernel doesn't know that there are 3 threads inside that process. Kernel thinks that it is just 1 thread, so the kernel allocates only 1 CPU for this process. So these 3 threads are sharing the same processor, even though I have 3 more processors are available, okay? Even though I have 3 more so the processors are sitting idle, and these 3 are trying to use the same processor. So I cannot take advantage of multi-processor systems if I implement everything in the user space. That's why later they have invented this. They say that, okay, I am going to support kernel, or I am going to support threads at the kernel level. So this kernel knows that I have 2 processes, process 1 and process 2, and I will keep the process-related data inside this. Thank you. Inside this process table, 2 entries. But I know that this process has 3 threads in it. So let's say this is T11, T12, and T13. Again, okay, so total of 7 threads, and I have a thread table at the kernel level from 1 to 7, okay? So the kernel knows about the threads. If one of the threads is blocked, let's say this one is blocked, it is reading some data from the disk, kernel knows that there are 2 other threads inside the same process, they can continue running, okay? And let's say I have 10 processors on my system, 10 CPUs on my system, 10 cores. Kernel knows that there are 7 threads running, and the kernel can assign these threads to the available CPUs, okay? So these kind of advantages are valid for this approach, kernel level implementation of the threads. But what is the disadvantage of this picture? Yes?
Maybe scheduler does not decide to return to the first process.
Yeah, the scheduling is not as flexible as this one, right? I mean, you are dependent on the kernel. I mean, kernel makes the decision, you have to obey that one. But what you are saying is not exactly valid, because kernel is smart enough to switch from this one to this one to this one to this one before switching to others, because it knows that there is a very serious penalty for the context switch between these 2 processes. Kernel knows that one, yeah. Kernel can take advantage of it. What is the other disadvantage of this picture? Yes?
Maybe parallel execution.
Parallel execution?
Yes, executing all the threads simultaneously at the same time.
Is it a bad thing?
No, advantage as an advantage.
I am talking about disadvantage. Yeah. If you have more than 1 processor, yeah, that's the advantage, yes. Yeah.
Maybe the processing the user mode should make system calls to access thread table.
Well, as a programmer, I actually don't care how it is implemented. I am just calling these functions, and some of these functions it results in a system call. Some of them they don't. I mean, is that your point? I mean, as a programmer, I have to write my program differently for the kernel level threads. Is that what you're saying?
No, but maybe system calls be less efficient.
Yeah, exactly. Yeah. So that's the point actually. For this one, whatever you do with the threads, whether you are creating a thread or terminating it or yielding it, you have to make a system call. System call means context switch. Context switch means hit from the efficiency point of view. So it is inefficient to have library implemented using this way, because you keep doing this context switching all the time to do anything about threads. So inefficiency, context switch time is the main problem of this picture, kernel level threads. Okay, so these are the advantages of the user level threads. Okay, the disadvantages, of course, the blocking system calls. Page faults. Page fault is, I mean, one of the threads needs some memory data, but that memory data is not available on my memory. It is on the disk. It has to be loaded from the disk. So who's going to load it? Operating system, and operating system blocks me the whole process, including the other threads. So that's not going to be good. So blocking system calls, page faults. Okay, these are almost the same thing maybe. And multiprocessor CPUs, I cannot use them with the user level threads. Okay, and other kind of stuff are the problem. So we talked about this, we talked about that. So the solution is, let's use this picture, kernel level threads. Okay, so the kernel manages the thread to create, destroy, originate the thread. They are all done by the kernel. And similar, like the process table, we have a thread table now. It is integrated with the process table, but it's a thread table. Okay, so the kernel is larger now. Kernel uses more memory because it has to handle the kernel thread level information. But we have solved this blocking system calls. I mean, I'm not going to block the whole process because one of the threads of that process is blocked. I know that there's a kernel. That's okay. And I know that there are n number of threads running. So if I have more than n processors available, I can distribute them amongst the threads, no problem. But again, thread switching is expensive. Okay, because it needs context switching most of the time. And anything about that I'm doing with the threads is going to result in system calls, which is context switching, which is copying of data across the protection boundary. So those are the disadvantages of kernel level threads. Okay. So what do we do? One solution is this. They say that let's implement both. Okay, kernel knows about the threads. Okay, so kernel knows about the threads, but inside my process, I have my specialized thread processing library too. Okay, so kernel tells me that, okay, you have 2 threads inside this process. Kernel thinks that there are 2 threads inside that process, but I am using this thread to manage 3 user level threads, and I am using this kernel level thread to manage 2 user level threads. So switching from this one to this one, or making these kind of threads, is very easy because I don't need any system calls. Okay, but if this one is blocked, that means that this kernel thread is blocked, but this one can continue, right? So it's kind of again, it's an hybrid approach. Advantages and disadvantages kind of managed together. There is a trade-off. Okay, so even though I am running 5 threads inside this process, kernel thinks that I am running 2. Okay, so the effect of those blocking is kind of 50% less than the other ways. But since I am not overloading the kernel with 5 threads, I am using the advantage of user level threads too. This is called hybrid implementation of the threads between the kernel level threads and the user level threads. Okay, good, yeah.
Is there any disadvantages about using single process on hybrid implementation?
Is there any what?
Disadvantages of using single process. I mean, there are
Single process, single thread?
there are 5 threads, right? But there's a single process. Is there any disadvantages about it?
Well, we talked about why we are using multi-threads inside a process, right? Last time, yesterday. These threads are helping each other, right? That's the idea of using threads, more than one thread. Your question is, why are we using a single process?
Yes. I mean,
Well, I can have another process here, another is a process too. I mean, if you like, P1, P2, and P3. And this one has many threads like this, but these 3 are one kernel level thread, and here one thread, and this one is connected to just one kernel level thread. So this could be the picture. I mean, okay, did that answer you?
I think he says, what about if there is only one thread to handle all the threads in one process?
Well, it is up to you. You could do that too. I mean, you can do, let's say I have 5 threads like this, and all of those are connected to one single kernel level thread. As a programmer, it is up to you to make that decision. I mean, if you like, you can assign a single kernel level thread to one of your user level threads. Okay? But you know the disadvantages and advantages. If you have too many kernel level threads in your process, that means that context switching will hit you. Okay. If you have only a single kernel level thread, then the blocking system calls will be a problem. So the user of this picture, of this kind of architecture, thread architecture, knows the advantages and disadvantages of both worlds, and is trying to achieve a trade-off. Correct number of user level threads and correct number of kernel level threads. Good? Okay, so these are the hybrid implementations, and there are some other approaches for this problem. Let me talk about those. We looked at this hybrid type of implementation. Then let's look at these scheduler activations and pop-up threads. Okay. So the schedule activation is this. Some operating systems will tell you this. Okay, I made a system call. I make a system call. For example, read from the desk. Okay, read from the desk. And our classical approach of system calls is that if the data is ready, it will give you the data. Otherwise, it will put me in the blocked list, right? Blocked queue. That's what happens. But some operating systems tells me that I cannot provide the data for you right now, okay? But you can still continue running. Do whatever you want, but your data is not ready. When the data is ready, I will let you know, okay? If you have such a non-blocking system calls, okay, non-blocking system calls from your operating system, then your process can continue, right? So this is my process. There are 1, 2, 3 threads running, okay, and this is my kernel. This one said that, okay, read something for me. And the operating system says that the data is not ready. I will let you know when the data is ready. Okay, but you can continue running. So, well, this thread cannot continue, right? It needs the data, but the other two can continue. So my thread library inside this process can schedule another thread. Okay, of course, this makes my thread handling library much more complicated. and because it needs to, it needs to know that one of the threads are blocked and the others can continue, and etc. Also, when the data is ready, I will get that information from the operating system, and that relies on up calls. Okay, so operating system is kind of making a call to the process. Just, we never did this before. Previously it was like a function call and it returns, function call and it returns, right? When the data is ready. This time it is not like that. Sometimes operating system is calling me, okay? And writing such code is not that easy, of course, and some people don't like this at all. They say that this is not like, okay, I have hardware at the bottom, then the operating system, then the libraries, then the user programs, and the communication is always like this and that, okay? I ask something, and I wait until it is ready, etc. This is not happening anymore. I am asking for something, it says that the data is not ready, you can continue. So kind of two things are, operating system is running in parallel with me without satisfying my requests. It's not that easy to write code for this kind of stuff, but it is available. It's called up calls or the schedule activations. And as I said before, it is kind of tricky and some people don't like this. Okay. So normal user programs call functions in kernel. Sometimes the kernel calls a user level process to report an event. Okay. So some people don't like this. Okay. This usually violates the layering approach. This is called the schedule activations or up calls. Okay, so I am not going to talk much about it, but this is a way of solving problems with the blocking system calls. We will come to this problem, blocking system calls. Sometimes we need this, sometimes some programs to some restricted extent need to know if a system call is going to block or not, okay? I am asking the system, operating system, if I ask you this data, would I be blocked? An operating system is nice enough to let me know that yes, you will be blocked. Okay. In that case, I am delaying that one. Okay, I am doing something else. Well, it makes writing programs a little bit more difficult, but it is better than getting that performance penalty, right? So those are called schedule activations and up calls, and I'm not going to talk much about it. Okay, so we talked about the implementation of the threads, user level threads and kernel level threads. Usually, remember, let's remember our thread library table. Okay. When you use threads like this, all you have these functions, and usually you don't care if it is implemented in the user space or the kernel space. So it's an implementation detail. I just call this function, and this function. The rest of it is handled by the library, thread library, and the operating system. So why are we talking about it? Because we are trying to analyze the operating system. We are trying to see how the operating system works. And this is a very nice picture, actually, this one. To understand what a thread is, to understand the relationship between thread and a process, to understand the cost of the context switching, and to understand the blocking threads and etc. So this picture is really nice to understand these kind of concepts about CPU abstraction. Remember, this is chapter number 2, and we are still talking about abstracting the CPU, the idea of threads and the processes. That's why we like to talk about this picture. Okay, and again, what was the classical problem for the operating system, people? What is the difference between threads and the processes? Another classical problem is, what is the difference between the user level threads and the kernel level threads? Okay, they will ask you to tell you the difference between those. Not that because it is important to know the difference in terms of writing good programs, but it is important to know the difference, and that will tell you how good you are at understanding what an operating system does for process scheduling, what an operating system does for thread scheduling, and their differences. Good, okay, so let's talk about, we said that one of the advantages of one of the largest or the biggest advantage of having threads is that threads they share address space. So the same memory address space, we like this. It is very easy to communicate between the threads in that way. So one thread writes data to some global variable, the other one reads it, right? So this is an advantage. But this advantage sometimes is kind of tricky. We need to be careful about this, okay? Sometimes this might produce undesired problems, and we are going to look at those problems now. But before that, maybe I should take some break. If you don't have any questions, let's take some break. Okay, let's be here around 11:33. After that, we will continue.
Hocam,
Evet.
ne dersinde karşımda sunumu Türkçe mi hazırlamamız lazım yoksa İngilizce mi?
İngilizce.
Sağ olun hocam.
Ha, ders İngilizce.
Hocam imza
İmzalar geçti. Ne zaman geldin?
20 dakika geç kaldı mı?
Tamam, o zaman imzalamayacaksın.
Geçen sene aldım da. Yok ama finalde farklı proje yapmıştım. Siz de beraber yaptık. Hem final hem proje var. Bize final proje yapmıştım. Proje kolay. Geçiyorsun. Projeyi yaptığında geçersin zaten. Finalde böyle ben sınıfta yapıyorum falan sonuçta. İşte yaparsın falan. Onu hatırlıyorum. MySQL'le çok karmaşık olmayan, tabii belirli miktar karmaşıklık istiyor da database kurmuştum, normalize olmasını falan istiyorum. Çok zor ders değil, BB falan aldım. Computer çok zor. Computer graphics. Bir tane falan da böyle yapmıştık. Oydu. Şöyle kolay böyle. OpenGL'de miydi neydi? Direkt şey çiziyorsun. Ev çiziyor. Paint gibi. Hiç boyutlu. Ray tracing'i falan anlatıyorlar.
Bir şey söyleyeceğim. Yarın bir tane sonları var ya. Nasıl bir son yapman lazım? Uyuyor muydun?
O derste hiçbir şey öğrenmeden geçtim.
Nerede yazmışsın görmüyorsun? Seste misin şu an? Ha, tamam.
Evet.
konuyu mu açık? Ne yapacağımı mı sorayım?
Matematik kahvesi yapmam gerekiyor. Bu bir şeyler söylüyorsun. Şuradan şimdi geçiyorsun.
Aynen. Biraz fizikten bol geçersin.
Hayır. Yok mu? Nerede? Tamam, onu hallederim. Onu hallederim. Tamam. Tamam, çok iyi oldu. İyi bir şey daha geçen neden geliyor? Bu hafta geliyor mu? Belki ben Afrasya'nın şeyine başvurdum. Sen şeyine. Bana bir şey yaptılar. Ekstrem yaptılar da beraber yapabilecek. İki hafta süresi var bu sabah yani. Hafta sonu yapalım. Çünkü sistem ödevim var. Tamam. Sağ ol. Teşekkür ederim. Sağ ol.
Gelmemek yani. Hemen konuya konuşmak çok sıkıntı. Yani bu tasarım geçirmek isterim. Zaten tarafı almıyor. Onun önünde oturmuyor rahat. Hiç ona benim işime giriyor. Hiç yapma olacağım. Deneyim yok. Zaten yakıtını sağlıyorum. Sana bulaşma. Şey gibi. Eğitimli bir başlayamadım. Çok iyi. Derslerden sonra onun sonunda gitti. Ondan sonra odaya gittim yani. Ortamda. Ondan sonra post videosunu izledim. Ben sonra verdim. Çok şey. Almanya'da. Onu izledim. Onu da Gebze taraftarı izledim. Sorgulayamıyorum. Bari biraz almamaya çalıştım dedi. Onları izledim. Ondan sonra saat 8'de dörtme için toplamıştım artık böyle. Tam o bitmeden çıktım. Bitmeden çıktım. Saat 10'a büyük saat. Olan bir dışarı kadar sürdü. Ben her şeyin aklımda nerede? Hiç kadar bakamadım. Bugün de tekrar bir şey çıkarsa sıkıntı olacak. Yani yazman lazım. Benim iyi perşembe akşamı maçı izliyoruz. Evet. Devam ederse bunlar daha önemli. Yani bunlar Daha değil çünkü. Yani zaten tekrar alabiliyorsun. Tekrar şampiyon olabilirsin. Tekrar mahkum edileyemezsin. Tekrar şampiyon olur musun? Tekrar yok mesela. Maç eğer kazanırsa değil. Ben geçen baştan numarasını izlemek için hiç puan almadım.
Okay, so we like multi-threading, we like multi-threaded applications, but we have to be careful about some problems. We said that each thread has its own stack. Okay, that means our local variables are separated. That's nice, no problem. If I have a function with parameters and the local variables, since I keep them on my own stack, I can call the same function from different threads and it will work fine. But if those functions are using the same global variables, then that's going to create a problem. Because we will have these kind of problems. For example, thread number 1 and thread number 2. Okay? Let's say I have a global variable, error no, int error no, okay? It's a global integer, and thread number 1 it works, okay? It accesses the error no. Let's say at the beginning, okay, the error no is 2, error number is 2. Okay, this thread number 1 accessed it, okay, accessed it, and it made it 3. Okay, soon after that there is a switch occurred, thread switch occurred, and thread 2 is running. Thread 2 started running and it accessed the same error number and it made it 4. And another switch occurred and thread 1 is running. And thread 1 reads error no, it is expecting to find the 3, but there is 4 there. So it looks like, I mean, both of them are trying to manipulate the same global variable, and they don't know the other one is working on the same global variable. And it's going to cause lots of problems for these. And it is very difficult to understand what is going on because these kind of problems happen very rarely, but when it happens, it is difficult to find what's going on, because next time I am running these two threads together, this may not happen, right? Because this switching time back and forth, it doesn't depend on me. It is up to the thread library or the operating system. So it is important to know these kind of problems. So if you have a global variable in your thread, in your function, if you are modifying it, then using such functions in multi-threaded applications has to be done very, very carefully, or just eliminate altogether global variables. We don't like global variables at all, okay? And this is another reason for not using the global variables, because they are not safe in terms of multi-threading. And you might say that, well, I am not using the global variables much, but there are some C functions that use the global variables a lot, okay? Some of them are like, for example, str tokenizer, okay? str tokenizer. It uses some static variables in it. What's a static variable? Static variable is just a global variable, actually, right? Inside a C function, if you have a static variable, it's a global variable, and if you keep using this function from two different threads, then you are modifying the same global variable, and that's going to mess up your functions if they are multi-threaded, okay? if they are multi-threaded. And that's why we say that not all library routines or library functions are prepared for using threads this way. And the static variables, global variables are main causes of these kind of problems. So it is not just you are writing functions that don't use static variables or the globals. It is the libraries that you are using. So you should be careful about what kind of functions you are calling. The functions that you are calling must be re-entrant. Re-entrant means that, okay, everything they use, these functions, they either come from the parameters, which are our local variables actually, or they're local variables. So they all have to be kept in the stack. So they are the re-entrant routines. Okay, re-entrant routine means that can be invoked more than once simultaneously without any problems. Okay. So for the re-entrant routines, there should not be any statics in it. There should not be any modifications of global variables, right? Well, I mean, this is fine. If you have a define size 10, this is not a variable, this is a constant. Nobody is going to change it. Okay? So use this size as much as you can, as long as you don't make any change. Well, I mean, obviously you cannot change the value of size. It is defined, right? Or a constant integer global. That's fine. But global variables that can change values are very problematic for multi-threaded applications. Again, the fact that the common address space is becoming a problem because these kind of stuff can happen with the global variables. Two different threads are modifying the same thing. You might say that, well, this is how I communicate between the threads. Okay, one thread is writing to this global variable, the other one is reading it. Okay, that's called the interprocess communication. Okay, and it has to be done in a very, very careful way. And if this is not the intended way of communicating between the threads, then that's called a race condition, and that's not a good thing. That's why we would be very careful about, okay, just modifying your single-threaded code into a multi-threaded code. You might get surprised that your perfectly running single-threaded code is giving you lots of problem when it converted into multi-threaded code. Okay, and most of the problems come from the global variables and static variables. Avoid using those kind of functions, or avoid writing those kind of functions. Okay, good. So you learned another bad side effect of using global variables. Good. So I talked about this, and we talked about the re-entrant routines. Many C library routines do use static buffers, unfortunately, because I mean those C functions, they were designed in 1970s. In 1970s, of course, we had the multiple processes available, but I mean, we don't have this problem with the multiple processes because between different processes, we have the address space isolation. They have their own global behaviors, right? So no problem. But as soon as they have invented multi-threading in 1980s, okay, these kind of functions started creating problems for the multi-threaded applications, because statics basically mean global variables. One such function is this local time. What does the local time do? Okay, local time does this. Okay, you call local time, it returns you the time of the day. Okay, time of the day, but it returns it in an allocated global variable. Okay, so you pass a pointer and it makes a new, I don't remember exactly, but it makes a dynamic allocation and it returns it returns the result to you. Okay, so this is a problem because if two different functions call this function, okay, and you are modifying, if you are trying to allocate space globally out of this function, that's going to give you a problem. So instead of writing these kind of functions, write a function like that. Okay, allocate your space yourself, okay, and send the pointer to this function and let that function to modify it. Okay, so don't let that function allocate space for you and return the result. Do your allocation yourself, keep your pointers in your stack, and send those addresses to those functions as local variables or the parameters. Okay, so that's one example from the book, I guess. Okay, as I said before, what kind of other, I am sure there are lists of, I didn't try this, C functions that use static locals. Okay, what is the use of static keyword? What are the local static variables inside a C function? List of C functions, maybe. I couldn't find it. Static functions in C. Couldn't find it. I thought that there would be a list of functions that tells you which C functions use the statics in them. str tokenizer is one of them. The other one is maybe that's the local time. No, well, these are just simply explaining the stuff. Anyway, so maybe if you make a more detailed search, you are going to find them. So avoid those functions. Don't call those functions. Don't use globals. Don't use statics. Always use your stack. Always use your local variables and your parameters to pass information to your functions. That's what I'm saying. And these are the rules for writing good programs, also writing good multi-threaded programs. Well, I mean, if you need global variables, there are ways of dealing with it, but I am going to skip this part. Okay, now let's talk about this interprocess communication. I mean, that's maybe the main reason of making these threads. One of the main reasons of making the threads. Let's communicate between the threads. Okay, let's say one of the threads is making some data, and the other thread is using it, such as I don't know what, but remember this. I mean, these are two processes, but you may think it like that. I am doing this ls or ll. Okay, so this is one producing some results, and I am going to feed the output of this one to the word count, program word count. Okay, ls is producing one output and word count is consuming that output. One of them is producing, the other one is consuming, right? I mean, this is not a very good example, but I mean, because these are two separate processes, maybe I like to do the same thing with the threads, and one of them is producing something, the other one is going to consume. Okay, and we are going to see some examples of it, simple examples of it in a few minutes. So I like to do this. This is called basically interprocess communication. Well, I mean, don't let this term process, interprocess confuse you. The same technique can be used between the threads too. So we generally call it interprocess communication, but we use the same kind of technique, same types of techniques for communicating between the threads. Okay. So when it comes to interprocess communication in general, okay, there are three issues. The first one is, how can I pass information from one process to another, or one thread to another one? This is easy for the threads. Why? Because threads share memory space. Okay, you just modify a global variable and that's it. The other one can see it, okay? But we have to be careful about that one, okay? For the processes, how can I pass information between the processes? Like this one, like the one that I showed you like 1 minute ago. Use these kind of operating system specific ways of handling stuff, okay? Use a specialized file, pipe file, or use a regular file, or sometimes operating systems will give you special places in memory, and those places can be shared between the processes, okay? So there are ways of doing it, but it is very easy to pass information between the threads because that's the whole point of threads actually. The second is that, okay, the second issue between, about interprocess communication. While I am modifying the same shared position, okay, I should not get in others' way. What do I mean by this? For example, I have two threads, two client threads, okay, trying to make a reservation for a passenger of an airline, and two clients are trying to grab the same seat at the same time, okay? So the seat is available, and both of them trying to get the same seat, and both of them thinks that they got the same seat, they got the seat. That's going to be a problem, okay? And so we should be careful about this. So if both of them are working on the same data, we should be careful about the side effects of it, okay? And the third one is, which is called the race condition actually, proper sequencing when dependencies are present, okay? If process A produces data and process B prints them, okay, B has to wait until A produces the data. B cannot continue until the data is ready, right? Okay, A produces the data, B consumes it, like the ls program. It produces the list of the directory. WC has to wait for its output. So WC cannot say that, okay, I am done, I didn't see anything, 0 lines. You can't do that because ls did not finish yet. Okay, so that's called the proper sequencing. I have to wait until the data is ready. I have to wait until the data is ready. So I am going to look at these issues one by one, but for the first one I am going to skip it because for the processes it is just as simple as sharing the same global variable. Let's look at the second one and third one, and let's see why they are so important problems, okay? So let's make this definition race condition, okay? One of the important problems of having multi-threaded applications or multi-process applications that share the same data is the race condition. Race condition is a bad thing, okay? It is bad. And the definition is this. If you have if you have more than one process or thread, okay, and these are sharing some global data, or they are sharing some data, and the final result of these both processes or threads depends on who accessed at what time, okay? So if you say that, okay, process A and process B, they are working on the same data, their final results should not depend on who accessed when, who accessed the data when, okay? It should be always, doesn't matter who accessed the data when, it should be always the same result. Either the A runs first or the B runs first, or while A is running, there is a switch and B started running, then the A is running. It shouldn't matter who runs first. It shouldn't matter what kind of switching happens between A and B. It should not matter. My result should be exactly the same. If my result is not exactly the same, then there is a race condition between these two processes or the threads. It's called the race condition, and we don't like race conditions and we have to deal with it. Let's look at one example of a race condition, a spooler, okay? Spooler is this. Remember the spooler, especially the print spooler? I am not sending anything to the printer myself as a program. as program A or process A and process B, I write the name of the program to be printed on a special spooler queue, okay? Spooler queue has these three global data structure. One is a list of the files to be printed. The other one is the position that is available for me. For example, this in 7 is the slot number 7 is available. As a process, I can write my file's name in the slot because the slot number 7 is available. Process A and process B can write their file name in the slot. And the out is the first file to be printed. So this out is used by the printer daemon. It just says that what is the out number 4? So I am going to print this one. After I am printing this one, I am going to out number 5, program C, then the program N, whatever. Okay? So when in and out is the same thing, that means that the queue is empty, right? I don't have anything to print. And if I have a process to print something, I simply come here. I'm going to write my file name, test.s, whatever, okay? And where should I write it? You should write it at this position N. So global variable, and global array. So we have to be careful about this. Well, what did I say? Avoid using global variables. Well, in this case, I have to use it because that's the only way to communicate between the processes. So let's see what kind of problem I can have here. So process A and process B are trying to do, I try to run these simple lines of code. And both of them have access to these 1, 2, 3 global data structures, 2 integers and 1 string array. Okay. Let's say process A is running. Okay. Process A said that I am going to write file A in this position, buffer N. N is 7. Buffer is here, so I am going to write file A here. I wrote it. Okay, that's fine. Okay, now I am at this position. Out of bad luck, and that's going to happen, a process switch happened. Okay. I got a timer interrupt, and operating system decided that process B should run now. Okay. So when the process B is running, it will say that I am going to put file B in this position, buffer N. Remember, I put file A in this position, but before I had a chance to increment the value of N, a process switch happened. Now process B is overwriting this, saying that I have file B here. And then I am incrementing this N by 1. So N becomes 8. And then when I come here, okay, when I come here, switch happened again. Whenever the switch happened, I come to this position, I incremented in again, in became 9. So in is pointing to this location. So what happened? What's going to happen now?
Well, basically we lost file A.
Are you talking? Yeah, say it again.
We basically lost file A.
Yeah, file A will not be printed, right? So the process A says that, okay, I'm not going to print anything. I'm not saying what happened to my file. I send it to the printer, to the spooler. It's not printed, but the other thing is that the spooler thinks that there is a valid file name here. Okay, there is a valid file name here, but there is junk. Okay, it will try to open that file, and it cannot open. Probably the spooler will crash, maybe because it does not open it, or if out of bad luck, it will open a valid file, and it will print something large for you, and everybody will get surprised. Who's printing this large file? Okay, So this is a race condition. Why do I call this race condition? It is because bad things happened. It is no. Well, the bad thing has happened, but it is not because bad things happened. It is race condition because the output of this whole thing, process A and process B running, depends on who is running first and when. Okay, if I did this, okay, if I run this one, then switch happened, run this one and run this one, it is fine, right? File M and file B will get placed into my spooler. Or if I run this one first and then after run this one later, again, no problems. It will be the same thing. Both file M and file B will be printed. But if I have this kind of switching order, write this one, switch, then this one, then switch this one and this one, then I mean, depending on who is running when, is going to create different results for me. And some of these results are very, very bad. This is a race condition. We don't like race conditions. Okay? We don't like race conditions. You cannot avoid race conditions all the time, but you can most of the time, okay, most of the time, you can prevent having these kind of bad results out of the race conditions. That's what we are going to do. Okay, the solution for these race conditions, the problems with the race conditions is to create mutual exclusion zones. What we need is mutual exclusion. That is some way of making sure that if one process is using a shared variable or file, the other process will be excluded from doing the same thing. Okay, so you are going to say that between these two lines, this is my mutual exclusion zone. This is my mutual exclusion zone. Okay, if I am inside this region while I'm executing this, nobody can use these three global variables. Only I can do it. So I am mutually exclusively, okay, have the right to modify these three variables if I am within these. Okay, so it's going to be like this. I am running here. I executed this. I have right to modify this buffer because I am in the mutual exclusion zone. Okay, I am modifying it, and a switch happened here. A switch happened, and I started running at this position. I cannot go into this mutual exclusive zone because A is in there, okay, so I will be blocked. B will be blocked because operating system knows that it is a mutual exclusive zone, mutually exclusive region, critical region sometimes we call it. So B will be blocked, and A will start running again. A will do this, then E will do this, and it will say that, okay, I'm done with the critical region. If anybody wants to enter the critical region, they can. Okay, so this is called mutual exclusion or the critical region, and that will be the basic idea of preventing the bad side effects of the race conditions. Okay, critical regions. And how are we going to do this critical region thing? Of course, we need the help from the operating system most of the time, because operating system knows both of these processes. Operating system is going to give us some mechanisms to specify the critical regions. You are saying that, okay, I am in the critical region. You are telling this to the operating system. Operating system says, okay, you are the only one that can be in that region. And here you are saying that I am out of the critical region. Okay, if anybody wants to enter the same critical region, operating system will block that process. They cannot be in the same critical region. Okay, so mutual exclusion is some way of making sure that if one process is using a shared variable or file, the other process will be excluded from doing the same thing. That's the concept of mutual exclusion. And coming from this mutual exclusion area, with the help of the operating system or some kind of helper library, okay, part of the program where the shared memory is accessed will be called critical region, okay, or critical section, and operating system will help us define these sections and enforce these kind of mutual exclusion zones rules. Okay, so then we are going to see, first we are going to see how can we do this without getting any help from the operating system. Then we are going to ask the operating system give us some help, An operating system will tell us that I can do it, but if I can get some help from the hardware, CPU help, I can do this even better. So at the end, you will see that they had modified some of the instructions of the CPUs so that I can do this critical region thing with the help of the hardware and operating system, helping me in a very efficient way to achieve these critical regions. The fact that I can specify the critical regions very easily doesn't make multi-threaded programming or multi-process programming with the interprocess communication easy. There will be lots of other problems, and we are going to see them one by one. Okay, so what did I say? I mean, after introducing the idea of the multi-processes and the multi-threads, now we started using these ideas, but we need to solve the resulting problems through the interprocess communication. That's what we are looking at. Okay, so the critical regions. Okay. To avoid race conditions, with the help of the critical regions, okay, we need to be careful about these conditions, okay, These are the requirements. If you define a critical region, the number one rule is no two processes may be simultaneously inside their critical regions. Okay, number one rule. This should happen. Okay, so if this is my critical region here, okay, CA, critical region A, and this is the critical region A for this process. If I am inside this critical region, if I am executing this region, process B cannot be in the same region. Okay, so that's the rule number one. That's obvious, right? That's obvious. Well, that's not it. There are other rules. Number two is no assumptions may be made about the speeds or the number of CPUs. You cannot say that, okay? You cannot say that my CPU is so fast. This is just 2 lines of code. My CPU will be so fast, it will run through this region in a matter of microseconds, and nobody can do the. I am not expecting any switching to other processes while I am doing this. You cannot assume those kind of stuff. You cannot say that process A is so fast, the priority is so high, I assigned it a separate CPU, so no such thing as switching while during the critical region can happen. No, you can't say that, okay? You will not make any such assumptions. So you will not say the chances of having a process switch from A to B is one in billion, right? You can, well, that's true, maybe 1 in billion, but that 1 in billion will happen in 1 or 2 days. When it happens, what happened? Somebody's file is get lost. If that person didn't have the backup of it, we lost everything about that file. And on top of it, I printed something junk. Maybe my printer spooler crashed. And you are going to look for this error for a month, and you will not find it, and your customers will not be happy. Your boss will not be happy, and etc. and etc. So the results are sometimes very, very, very, very bad. So no such assumptions. No process running outside this critical region may block other processes. So you can, let's say this is A, inside A, this is my critical region, this is process B, this is my critical region. If A is here, okay, or if A is there, it's running there. If B is here, you cannot make B wait in front of the critical region if the A is not in the critical region. So if nobody is in the critical region, then B should not be blocked. No processes running outside this critical region may block other processes. And sometimes you might say that, okay, what is wrong with this rule? I mean, who makes such a blocking? But sometimes this happens. Okay, And number 4 is actually the obvious thing, but sometimes what happens if I block both A and B? I mean, I am blocking both of them. Nobody can enter the critical region, so no race conditions that I prevented them. Of course, don't do that. That's what it says. No process should have to wait forever to enter its critical region. Okay. So if you block everybody from entering the critical region, you solve the problem of race conditions, right? But you kill all the processes. Then what is the point of having multiple processes then? Okay. So we are going to see cases where some of these rules are violated, and we are going to try to handle these cases one by one. Okay. Any questions so far? Okay, let me move on. More examples, maybe. Okay. Process A and process B. Process A is running at time t1. Okay. It enters the critical region. While it is running, let's say process B. Let's say process B. Well, we don't make this assumption in this chapter, but let's say we have two processors, and process A and process B are really running in parallel on two different processors. While process A is running, it entered its critical region, and process B is running. Process B tries to enter the critical region, but it will be blocked because A is in the critical region. It is modifying some global variables and etc. Okay, so B will be blocked until A exits the critical region, and then B can be unblocked to complete whatever it wants with its critical region. Okay, so that's the idea. So mutual exclusion. Why do we call it mutual exclusion? Either this one or that one. Both of them cannot be in the mutual exclusive region, critical region. Only one process can be in the critical region. By the way, I keep talking about two processes, but there might be more than two processes, 3, 4, 5, 6, n processes. You might say that out of n processes, only one can be in the critical region. Okay? So the operating system or whatever your interprocess communication library has to satisfy all of these conditions. Okay, so these will be the methods that we are going to use to achieve mutual exclusion critical regions. Okay, we are going to look at them one by one. Some of them are not used at all. They are just there to tell you what's going on. What was the earliest solutions about these critical regions and the interprocess communication? Some of them are being used today. This one, the TSL instruction, when they have implemented this instruction on CPUs, and it helps us achieve these critical regions, mutual exclusion. And that will be the structure of the lectures for next week. But for now, I am going to, I guess, stop. Well, I mean, let's look at this one. How I can achieve critical regions. Disabling interrupts. There is a special instruction for the CPUs that disables all the interrupts. Okay. When process A enters this critical region, it disables all the interrupts of the system. So when I disable the interrupts, that means timer interrupt will not happen, right? Timer interrupt will not happen. Hard disk interrupt, keyboard interrupt, network interrupt, nothing can happen, okay? If no interrupt can happen, then process A will keep using the CPU until it exits the critical region, right? So one way of achieving this mutual exclusion is disabling the interrupts. It might be a solution, but there is a very bad problem about this approach, is that that's a privileged instruction, okay? Process A cannot disable the instructions because it's a user level process. Disabling the instructions can be done by the kernel only, okay? I can't let a process disable the instructions. Why? Because if it disables the instructions, then it crashes then the whole system is down, right? Without the instructions, my computer cannot continue. My operating system is not coming back. So I can't let any ordinary process to disable instructions by themselves. So that's a bad solution. The second thing is, if we have parallel multiple processors, okay, this one disables the instruction for that CPU, but for the other CPU, things are still going on. Maybe I can lock the whole bus, the memory bus. If I lock that bus, disable the instructions, okay, I am going to stop all the CPUs doing from something useful, and I will continue. Maybe you could do that, but again, that's a privileged instruction. So that disabling interrupts without any restrictions is not a good idea. Okay, we have to find other ways of preventing other processes entering the critical region if I am inside the critical region. Good. Okay, so I will stop at this point. I will see you next week on Monday.